from Universitat Rovira Virgili in Tarragona, and he will tell us about the dynamics of the second map. Please.
Thanks, David, and also thanks to the organizer for giving me the opportunity to give a talk in this seminar, in this conference. And well, this is a joint project with Laura Gardini from Universitat of Urbino and Ernest Fontich and Xavier Jarque from Universitat of Barcelona. In this project, we consider root finding algorithm, in this case, the Secant method, as a global dynamical system. In fact, this is a quite old idea since, well, in fact, at the origin of the complex dynamics, also consider the Newton method as a dynamical system. But Newton method is one of the most powerful root finding algorithms in order to solve a nonlinear equation. For example, in this case, when you apply the Newton algorithm as a root finding algorithm, at every step you construct the next iterate using the previous one. This is using this function, this is the Newton map, and well, this is very common. But when we mention here is that at every step we only use the previous iterate. That in the case of the Newton algorithm, we need the two previous ones. In this case, we consider that P is a polynomial, but this can be done in the same way with an entire map, and the dynamical plane is the Riemann sphere. Okay, in the dynamical plane, the focus on this kind of iterations, we know that the zeros of the polynomial are fixed points for the Newton map, and in this we can define A alpha, the set of points converging to a root of the polynomial. So for every root, you have the basin of attraction. These are obviously part of the Fatou set, and perhaps there are other behaviors, but this is part of the structure of the dynamical plane for the Newton map. Also, we define, or it is defined, the immediate basin of attraction as the connected component of the basin of attraction containing alpha. Well, as I mentioned, the Newton map is the most studied case, and there are a lot of people that has been working in this problem. I quote here a list of some of them, but perhaps, well, perhaps not. I'm sure that there are more other people that has been working on that, and they use different approach, they obtain different results, and well, a lot of work has been done on the dynamics of the Newton map. Just to show the dynamical plane, and I take an example of this. Well, it's a very trivial example, but it's a cubic polynomial with roots at simple roots at 0, 2, and 3. This is the expression of the Newton map, and well, later on we will apply the secant method to the same polynomial. So for this reason, I fix this polynomial, and here is a dynamical plane. Here we have at 0, 2, and 3 that are the roots. We have a fixed point for the Newton map, and we color in red points tending to the origin, in green tending to 2, and in blue tending to 3. And well, we will see in a moment a lot of properties of this dynamical plane, but for instance, the basin of attraction of the root located at 2 has only one component, and the boundary, we know that is the Julia set, and this Julia set is repelling fixed points are dense and has this fractal structure. And for the basin of attraction of 0 and the basin of attraction of 3, it's this is the immediate basin of attraction, and the other small red components are pre-images, and the same happen for the basin of attraction of 3. Okay, then assuming that P is a polynomial and we have the Newton method and the Newton iteration, let alpha be a root that could be simple or multiple. Here I list some basic properties about the basin of attraction of one of these fixed points coming from the root of the polynomial. The root belongs to the basin of attraction, and in fact it has a neighborhood of points converging to it. This means that if you are close enough to the root, doesn't matter if it's a simple or a multiple root, you converge to the root. So this means that the method as a numerical method, it's well, if you start sufficiently close to the root, you arrive to obtain an approximation of the root. Second property is that the immediate basin of attraction is unbounded. This property is used by several authors to obtain a set of initial conditions converging to all the roots of the polynomial. So this property could be understood also as a powerful property to obtain all the roots of a polynomial. Also, the immediate basin of attraction is simply connected, and well, the boundary of the immediate basin of attraction of any of the roots are part of the Julia set, and repelling orbits are dense. In most cases, for example, assuming hyperbolicity, the boundary of the immediate basin of attraction is locally connected. Okay, these are, well, obviously there are many more properties, but we concentrate on this kind of properties since we would like to make something similar for the secant map. Well, here we fix P a polynomial, and then the secant method generates this sequence of numbers. The first comment on this is that at every step, xn plus 1 depends not on the previous iterate, as in the Newton, depends on the two previous one of xn and xn minus 1. So really, the secant method, it's a root finding algorithm using 2. So we need 2 variables. Doesn't matter if you consider the variable real or complex, but you need 2 variables. In fact, this is just the secant map, and this is the algorithm to go constructing the sequence. In a similar way as in the Newton, we define the basin of attraction of a root. So let alpha be a root of the polynomial. We consider the basin of attraction of alpha. But in this case, the basin of attraction of alpha contains all the points converging to the alpha alpha, because both iterates converge to the root. This means that the root alpha has a fixed point on the diagonal. And in the same way, the immediate basin of attraction is defined as the connected component of the basin of attraction containing the point alpha alpha. Well, we make an example. Here we see the expression of the secant. Just a comment. Here we see this quotient that x minus y over px minus py. This apparently, if x is equal to y, you have here 0 over 0. But this is not really the case, because the polynomial px minus py has x minus y as a divisor. So we can make this division and we can obtain a well, 1 over a polynomial is the result of this, of making this division. We can see in this example, this is the polynomial P. This is the secant map. The first component is equal to y, and then the second one is this expression. Then to make x minus y over px minus py, you need to compute expression of the form x to the k minus y to the k over x minus y. But this you can divide and you obtain this polynomial. So here, the term with x cubed minus y cubed is this expression, this symmetric polynomial of degree 2. And this is the symmetric polynomial of degree 1. And so, well, the same for this case. It's just a computation. Well, here is the dynamical plane of the secant map applied to the polynomial x times x minus 2 times x minus 3. As in the case of the Newton, points in red are points converging to their root 0 and the fixed point 0, 0 for the secant. The same in green for the fixed point at 2, 2, and the same for the third root for 3. Look that these 3 fixed points are located in the diagonal. And in this dynamical plane, what we see is first the existence of these lobes here. And if, well, we can make a zoom in a moment of this part, we see that there are more lobes. And also dynamically using just the expression of the secant, if you consider the root located at 0, the horizontal line y equal to 0 in one iterate maps all points just at the fixed point. This is because in the expression on the secant map appear the p of y. So if y is one of the root, maps here. Except at that point, because at that point is when we have the other root, x minus y is different from 0, but p of 0 is equal to p of 2. So there are one vanishing in the denominator. We will see this, I think, that more clear in a moment. Eh? But this is more or less the dynamical plane of the secant map applied in this case to a polynomial of degree 3. Also, here we see these white points that are points that does not converge to any of the roots. We also work and try to understand what happened at that white points. Okay, this is a magnification of this part. Magnification of this part, and we see one of these points when the secant map is not defined because x is different to y, but px is equal to py, and you see the lobes that appear at that point. This is exactly the same dynamical plane, only a zoom of that. Okay. Here we assume that alpha is a simple or multiple root, and what we would like to answer or try to answer or work on that is just the same list of properties that for the Newton map are well known and solved, the similar behavior, the similar questions for the secant. In this case, for example, we don't know if given a root, we always have a complete neighborhood of points in where the secant is converging to the root. Also about the immediate basin of attraction, if are bounded or unbounded. Remember that this could be useful to obtain initial conditions. Also, if the immediate basin is simply connected or not. Also, we are interested in who. This who means which dynamical object controls the boundary of the immediate basin of attraction of a root. In complex dynamics, this dynamical object is the Julia set. And well, a little bit about the local domain connectivity and what is the dynamics of these white points. Well, also, we comment that here it seems that the boundary are smooth, except at that points, at that corners where the map is not well defined, we would say. Okay, the previous works on that topic, this secant map is not bijective, so we cannot use anything related to automorphisms or bijective maps in C2 on R2, but we find a series of papers of Bisky, Gardini, and Mira about plane maps with denominator. It's a series of 3 papers. Basically, this is the dynamics of a map called T that writes, you can think that F is a polynomial in 2 variables, and this is a rational map, it's a quotient of 2 polynomials in 2 variables. So really the secant map is just a particular case of that behavior, so of that kind of maps. So we can take a look of that theory and apply to the particular case of the secant. Well, more or less at the same time that we are working on that problem with Xavi, Eric Bedford and Fritz work on the same problem in C2. Well, we work on different problems, but with the same map, but obviously there are some overlap, but no problem. We can explain, we can quote all the results that we use from this paper of Bedford and Fritz, and also the behavior. Well, in our case, since we are working on R2, we use more the reference about planar maps with denominator. Some basics about these planar maps with denominator. It's completely general, not only for the secant. It's applied with all the dynamical system defined in R2 with this expression. Remember that F, N, and D are polynomial. We can think that are polynomial. So the first is the set. Delta is the set where the denominator is 0. At that point, the first component has not problem, but the second one goes to infinity. And well, in the first step, it's possible to exclude all of these points and only consider the dynamical system T acting on R2 minus the preimage of all of these. What happens is that for the secant map, we can extend the map to this set, or at least for most of the points of this set. Okay, the second ingredient, and perhaps the most important, is the indeterminacy points. These are, well, the author also called focal points, but in the context of 2 variables, I think that the name is the indeterminacy points. Are points, a point Q is an indeterminacy point if both the numerator and the denominator is 0. This is really a point when the map takes the form 0 over 0. And at this point, the map is not defined. In fact, it's highly discontinuous. We'll see in a moment what happened and one of these indeterminacy points. And well, here Q is an indeterminacy points. I show here the curve delta. So at Q, the denominator is 0, but the fact that characterizes Q is that both numerator and denominator is 0. When suppose that we have a curve, gamma 1, crossing Q with one slope, for example, M1. Then, using this curve, it's possible to compute T and compute the limit at that point. And what happened is that the image is on one vertical line, why one vertical line? Because the first component has no problem. So if I take one of this curve, the first component is equal to f of q. That is the first component of the map T. But the second one, choosing a different slope, you arrive to a different point. So this is like why I put the word highly discontinuous, since using a different curve with different slope, we arrive to a different points in this line. In fact, the correspondence between the slopes and the values in this line is 1-to-1. Well, this line is called a prefocal line. And this phenomenon is the responsible to the fact that in the dynamical plane we observe the lobes. But I don't enter in details of this part. So we can apply this general theory of planar maps with denominator to the secant. In this case, in the case of the secant map, as we mentioned, the set delta, the set of no definition, are formed by the pair of points x and y such that are different, but the image is the same. In this case, the sum on the denominator is 0. And also when the derivative is 0, but that points are on the diagonal. We call these critical points that will play an important role. Also, it's very easy from the definition to obtain the indeterminacy points of the secant map. If alpha are the roots of P, the indeterminacy point have the components are equal to one of two, are equal to the roots of the polynomial. You can choose and you obtain these indeterminacy points. And the prefocal line is just a vertical line with the second component. This is because the expression of the secant map. Okay, in the same example, I show you the set delta S. The set delta S are the set where the secant map applied to this polynomial is not defined. This is just an ellipse, and these are the focal. In the next one, we will see better here. These are the roots and the fixed points 0, 0, 2, 2, and 3, 3. And at this set delta, here are the indeterminacy points. Look that the first coordinate is 0, and the first is 2, and the second is 0. And here the first is 3, and the second is 0. And the same happened in that case. So here we have this 1, 2, 3, 4, 5, 6 indeterminacy points. And here is the set where the secant is not defined. Also, we see that the set of white points also contains, in fact, this point, it's on the diagonal, is the critical point. Look that between these two roots, we have a local extrema, and between these two, we have another one. Here, we have one of these critical points, and here also. Okay, then at this point, we start to write the results that we obtain on this problem. And well, at the first one, we consider the secant map, and we make the difference and study what happens if the root is simple or multiple. Look that, for example, in the Newton methods, basically there are no difference. So simple root attracts with more speed than multiple roots. But in this case, if alpha is a simple root, the point belongs to the interior of the basin of attraction, but the case when we have a multiple root depends on the multiplicity. For odd multiplicity, yes, but for even multiplicity, the point belongs to the boundary. It's more or less like a parabolic point. We have here, we have a repelling direction. Well, the idea is quite easy. You only need to take the second component of the secant that is given by this expression and expand using the Taylor in two variables and study a little bit of that. It's not so difficult. Here is a picture. This is a dynamical plane of the secant map applied a polynomial of degree 4 with two simple roots here and here, green and blue, and a multiple root at 1, 1. In this multiple root, look that the point 1, 1 is not in the interior of the basin of attraction. It's possible to start very close to that point and not converge to it. So this is good news from the numerical point of view for the secant map near one of these points. Okay, this other result is just in, well, trying to put another result just in the same direction. At every indeterminacy points, Q, this point Q belongs to the boundary of all basin of attraction. But does mean that near an indeterminacy point, you can have initial condition converging to all of the roots. We don't work on that direction, but near an indeterminacy point is the good place to start to put a seed of points in order to obtain the roots of polynomial using the secant method. Just an example, here is the dynamical plane of a secant applied to a polynomial of degree 11 with 11 roots. In this case, is the Chebyshev polynomial. And for example, here in the top left, here it's a indeterminacy point, and here it's, you see clearly that close to this, you can obtain initial condition converging to the rest of the points. And a little bit of notation. If P has some roots, we call external the two roots with large and smaller value, and in the middle are called internal roots. And well, it's easy to prove that the internal roots, the immediate basin of attraction, is unbounded. For the internal is bounded. Basically, if you have an internal root, this means that you have an root to the left and one to the right, and then the dynamics on the horizontal and the vertical line at this level, alpha 3 and alpha 1, makes a box for the immediate basin of attraction of this of the internal root. Here, look that this internal root has close to it has involved these 3 indeterminacy point and these other 3 indeterminacy points. This is an example of the secant applied to a polynomial of degree 5, and here we see that these 3 internal roots, the immediate basin of attraction, the shape is more or less similar because this 6 indeterminacy point, look, that is like here is like one side, 2, 3, 4, 5, 6. We call like a hexagon-like polygon. The same happened for this root and the same happened for this root. And if you remember the dynamical plane with 11 roots, the 9 internal roots more or less are the similar structure. Well, we visit Laura at Urbino University, and she immediately asked which dynamical object control the boundary of the immediate basin of attraction. Well, since we are working basically on complex dynamics, it's from the point of view of complex dynamics, the boundary of the immediate basin of attraction is controlled by the Julia set. And well, it's full of repelling periodic orbits, but there are not something concrete to control. But she said that, well, we need to investigate what is the object controlling this boundary. And she proposed several objects that in other cases control the boundary of the immediate basin of attraction. The first candidate is the set of no definition of the map. This is this delta S. Remember that this is an ellipse for a degree 3 polynomial. But this is not the right one, because it's possible to extend the secant map to infinity. In what way? In the same way as in complex dynamics, using the map 1 over x and 1 over y. For example, if you take a point x naught, y naught in delta S, this point, after one iterates, the first component is y naught and the second component is 0. So using the chart 1 over y for this second component, it's possible to study the behavior. If you make this, the second iterate maps to infinity y naught, and the third iterate comes back to the finite plane. So if you take a point that maps to infinity, into 3 iterates, come back to the finite plane. So these are, and this, for example, can converge to the root. So the second candidate are these critical points. At these critical points, remember that belong to the diagonal. So at this critical point, when you apply the secant map 3 times, you has a 3 cycle, but going and back to infinity. In fact, this is part of the results obtained by Bedford and Fritz, that they prove that this 3 cycle attracts point from the finite plane. And this is these white points in the picture. But these white points are far to the immediate basin of attraction of the root, so they don't control this boundary. Well, another candidate could be the 2 cycle or the 3 cycle. And well, this map, the secant map, is very easy to see, that don't have nor 2 cycle, either 3 cycle, so it's not possible. But the secant map has 4 cycles, and this is what we study. 4 cycle. 4 cycle, well, just a notation: AB maps to BC, to CD, to DA, and AB. This is just if there exists one of these 4 cycles, and lambda is the cross ratio of this 4 cycle. Look that at this 4 cycle we have AB and CD are the 4 points working on that. So this is the cross ratio, and we prove that the secant map has 4 cycles and are of different types, and the cross ratio of these 4 cycles are these concrete quantities that are related with the golden number. Well, this means that at least there exist 4 cycles for the secant. Here is a proof, basically computing that the image of AB under the secant map is this point C. This is the expression of the secant, and manipulating this, you obtain this expression, and taking the product of all of these, we obtain 1, and this product that can be related with the cross ratio, obtaining basically the cross ratio of the 4 points. So we can classify, if there exists one of these cycles, we can classify basically using the relative position of the 4 points. We fix by symmetry that the smallest one is A, and then all the other possibilities. From these 6 possibilities are 2 that are not possible, and we obtain this 4 choice of the 4 cycle. Here, the first one are 2 points A and B with positive value of the polynomial, and 2 values C and D with negative value of the polynomial. So between B and D, at least, we need a root. So, well, we will see that this plays an important role because every root has this kind of 4 cycle controlling the immediate basin of attraction. Well, now we can prove that exists this 4 cycle. Basically, we fix 3 values, A, B, and C, equal to 1, 2, and 3. Using the cross ratio, you obtain the 4 point, and interpolating, well, fixing the value of one of the value of the polynomial at what point, we obtain the value of the polynomial at the other points. So we have a polynomial with 2 points and the image of these 2 points. So there are a polynomial of degree 3 interpolating these values and having a 4 cycle. That is important. We plot in the dynamical plane this 4 cycle, and basically what we see is that this 4 cycle, AB, BC, CD, and DA, are on the boundary of the immediate basin of attraction, are of well, we will prove later on that it belongs to the basin of attraction, but when we compute this 4 cycle, at least in this picture, we see the 4 cycle on the basin of attraction, on the boundary of the basin of attraction. Look that first we compute the 4 cycle and later the polynomial. If we make in the converse way, it's so difficult to obtain numerically this 4 cycle, since small errors in the numerics makes that the orbit converges to the root. So for this reason, we make in this way. Well, associated to this 4 cycle, we can compute the differential of the cycle, and there are one attracting direction and one repelling direction, and the stable manifold and the unstable manifold associated to this saddle point. And well, in this example, it seems that the stable manifold of this 4 cycle are the responsible of control the boundary of the immediate basin of attraction. This is like the philosophy of what we like to prove. Okay, this is what we are able to prove. Basically, we need to assume that the external boundary, if piecewise smooth, we put this in red because we think that this can be removed for the hypothesis, but not at that moment. And what is important is that if alpha is an internal root of the polynomial, the boundary contains a fourth cycle. And more or less the picture is one of here, it's to the left is the real one, and to the right is like the scheme of that one. Here we have this hexagon-like map with focal points at the vertices. We have lobes and 4 of the 6 vertices, and the most important, we have this 4 cycle on the boundary. But this 4 cycle, we prove this 4 cycle with topological arguments. So we don't know if, for example, has an central manifold instead of having an attracting one. So, but well, the idea, the conjecture that we have is that the stable manifold of this 4 cycle is just the boundary of the immediate basin of attraction. Well, just a comment. In the basin, in the working on the secant map of a polynomial, it is possible to obtain the boundary. Sorry, this is not the boundary, the immediate basin of attraction. In this case, not always the immediate basin of attraction is simply connected. This is basically because in the reals, we don't have the maximum modulus principle. So it's possible that a curve converges to 0, but the inside them go outside. In this case, we have a polynomial of degree 5 with 3 simple roots, is that one. Here in pink is the immediate basin of attraction. And here we see that this immediate basin of attraction is doubly connected. We have here a hole. Well, assuming the same in the same way that for the other proof, we need to assume that the external boundary is piecewise smooth, but we are able to prove that if there are 3 consecutive simple roots, and in this interval the polynomial has only 1 inflection point, then the immediate basin of attraction is simply connected. And this happened basically because the inflection points controls the degree of the polynomial. And if you have only 1 inflection point, then the degree is 1, and the immediate basin of attraction is simply connected. Well, finally, very, very quickly, what happened at a critical point? At a critical point, this is the white points are a 3 cycle using a normalization, and this is the immediate basin for this 3 cycle. We put the 3 cycle at 0, 0. And here is a thumb near one of these 3 cycles for a polynomial of degree 3, and this for a polynomial of degree 4 is just a thumb of the area. And here we use a result of Bedford and Fritz that they expand the 3rd iterate of the secant close to this to the origin that are the 3. Now for S cube, this 3 cycle, it's a fixed point, and this is the expression, and this expression has the terms until degree D plus other terms, higher order terms. And well, we consider the model map, and the model map is just the first part of this expansion, just until degree D. This parameter in blue encodes the behavior of the polynomial near 0 and near infinity. Remember that the cycle goes to near 0 to infinity and come back. So we only depend on the local behavior of the polynomial near 0 and near infinity. And we work with this map. Is a model map, is easy to compute. And well, the first thing that we did is to check if are similar behavior near zero, because we truncate on the terms of degree D. This is the behavior of the secant map near the origin, and this is the behavior of the model map T near the origin. It's quite similar, and also for the degree 4, degree 4. This is for the secant, and this is for the model. Well, the results that we obtain is that, well, this is still work in progress, it's not published, but what we think that we can prove is that if the parameter D is even, this is related with the degree of the polynomial, the basin of attraction of 0, these are the points in the secant that are the 3 cycle, is closed, bounded, homomorphic as a topological disk, and the boundary is the stable manifold of the origin. And here at the origin, we have an unstable manifold and the central manifold. And this is the boundary of this set. But this closed because one of the branches of the central manifold is repelled. And then in the other case, when D is odd, what happens is that there are a 2 cycle, and the stable manifold of these 2 cycle is the boundary of the immediate basin of attraction of these 2 cycle. And in this case, the boundary of this immediate basin of attraction is not locally connected. Basically, here we have a heteroclinic point that forces the stable manifold to oscillate strongly. And well, this is very similar to the horseshoe at this kind of heteroclinic connection. And that's all of the.
Muchas gracias, Tony. Are there any questions in the room? Nuria has one.
Hi, Tony. Thanks
Hi.
for a very nice talk. I'm just wondering if there is any chances to transfer these results to the non-model case, to the actual secant map, because they really look very. So what's the transfer, or what's the price you have to pay to go to the real dynamical plane?
Well, on one side is if, okay, for example, in that case, the local behavior of the origin, is, since it's an hyperbolic object, just move to the secant, but not the global behavior. So, well, these are only results for the model, but not for the secant. But in the next one, look that, for example, in that case, here
we don't see the transparent. You stopped sharing, so we see you, but we don't see. No. No.
Okay, in that case, working only on the model, we know that these 2 cycles control the boundary. So this has the intuition of what object you need to find for the secant. For example, this 2 cycle for the model is a 6 cycle for the secant.
Okay.
So perhaps only the intuition, but all of the objects that are far away to the origin, you cannot transfer to the original one.
Yeah, but the pictures look so strikingly similar, right?
Yes.
Even away from the origin.
Yes, because okay, what happened here for the secant? Points from here goes to infinity and come back, and really doesn't matter what happened outside. And this is just the behavior that encodes the model map.
Very interesting. Thank you.
Any other questions? Perhaps online, some questions or comments? Okay, if not, let's thank Tony again. Thank you to all the speakers of this morning.